Fibonacci or even the grid traveler, the move here is to actually start those other spots in the array at 0. Basically saying, at the start, I have 0 ways to generate these different prefixes of purple. And then as I actually find distinct ways, I'll go ahead and increment those spots in the table. But we'll get to that. And so we'll iterate through our table from left to right, of course, beginning at index 0 of the table. And as we do this, I'll also up top show the characters that we're considering within our table. Remember, the really important pattern here is when I'm at some position of my table, that means I'm encoding some information about the substring that starts at index 0 up to but not including my current index, right? So if I have some information stored at index 0, that information is about the empty string. From my current position, now I need to consider any words of the word bank that I can take right now to give me another spot within the table. In other words, since I'm at index 0, I need words that start with P. So let's say we looked at this first word of perp. And so if I looked at that word and I took it, that would bring me somewhere else within the table, right? I have to look forward like we usually do. So that'll end up at this position, index 4. Again, notice that we have the kind of off by 1 scenario here. So although I'm going to write information into index 4, that information is about the substring that spans from 0 up through index 3, right? And what I need to do now is take my current value in yellow and actually add that into my future position. So I just add 1 into the 0, and now index 4 contains a 1, right? Basically saying that so far we found one way to construct the string perp. And then from there, I look at any other words of the word bank that match, right? So I'll just look at the next word of P. Again, just moving left to right through our word bank right now. I'm still at my current position. And what I do if I use this P is I only look one character ahead, right? Because P.length is only 1. And what I do in this future position is, of course, just take my current value in yellow and I add it into this position. So 0 plus 1 is just a 1. There's one more word I can use right now from my current position. That's purple without the E. And if I look at that corresponding position, that'll bring me all the way over here. And again, I add the 1 into that position. Nice. I think that ends our very first pass. And now we move our current position to the right. So now my current is at index 1. So now I need to consider words of the word bank that begin with a U and kind of match characters throughout. The only option here is really just UR in the word bank. If I took a UR, that would bring me 2 characters ahead, right? So it would bring me over here. What I should do, like always, is just take my current value and add it into that position. So now I have a 1 over here. There are actually no other words of the word bank that match from my current location, so I can just move ahead to the next spot in the table. If we're at index 2, it looks like we need something that starts with an R. And there's actually no words of the word bank that we can use from this position. And what we also notice is there's also a 0 at this R position, so this wouldn't really do anything in our table anyway. So we can progress just to the next spot in the table. Here's where things start to get interesting, right? So right now, my current is at index 3, so I need to grab words from the word bank that start with P and potentially have an L and an E. So what I can do here is just take this lone P, which would bring me 1 character ahead. If I look 1 character ahead, what I do now is I take my current value, right, circled in yellow, and I add it into my look ahead value. So I increment that to 2 now. Nice. And then from there, I need to continue my logic by just moving rightward in my table, right? I shift my current point of view. At this point, what I do is I, again, look at any words that start with an LE. And there's really only one that matches perfectly. I look 2 characters ahead because the length of LE is 2. And what I do is I take my current value in yellow and add it into that position, right? My logic throughout this entire algorithm is very consistent. And there I have a 2 in the last spot. You could probably already foresee that we have our final answer, but if we continue the algorithm as normal, really we notice that if we move to the next position, there's no word of the word bank that starts with E, so I don't do anything here. And once we hit the very end, we're actually done with our algorithm. Right, and we see that, hey, we have a 2 in the last spot of our table, which is consistent with our expected answer. Something I think is really important to do is not only recognize that our final answer is in the last position of the table, but really any element of this table should make some logical statement about our target string, right? So let's say I look at index 4 over here. I see that there's a 2 in that spot in the array. So what is that really saying? Well, if I'm looking at the value stored at index 4, that means I'm considering the substring that starts at 0 and goes up to but not including 4. So that really means I'm looking at perp, right? And if there's a 2 inside of the spot in the array, that means that there are apparently 2 ways to create perp. And if I do a quick check in my word bank, that's exactly true, right? You can just take the straight up perp, because that's actually a literal word of your word bank, or you can do p plus ur plus p. Cool. So that's some consistent information. And then from there, if I actually consider what I can do from that position at index 4, well, you could have taken an LE. That's basically what we did when we traced through the algorithm. If you take an LE, then what are you really doing? Why is that value in the index 6 also 2? Well, for one, LE has a length of 2, so that's why I'm looking just 2 spaces ahead in my table. And if I think about what like logical operation I'm doing, if I were to take an LE and add it to all of the ways that I have in blue right now, then I would end up with all of the ways to generate purple, right, in my last spot. Literally just taking the LE as an additional move, right? Pretty elegant logic. Let's talk about the time complexity for this, though. So we know that, hey, our M is going to be the target, and N is going to be the number of words in the word bank. This is really going to be about the same complexity as our last rendition, right? That you can construct. So we're going to have M squared times N time, right? We definitely have M time for just iterating through every spot of the array. And we also have an additional N because we have to actually look forward for every element of the word bank. And so where does that final M come from? Like we've been saying lately, it comes from actually performing the match. I have to check for matching characters. In a similar way, the space complexity is just going to be M, really just based off of the size of the table. We're only ever storing just some numbers within this table, so our space just stays at linear O of M space. All right, I'm feeling good about this plan. Time to code it up. All right, let's code this one out. I'll start by creating my table. It's going to begin as an array with roughly target length size. Really target length plus 1. That way the index aligns, right? I'm going to fill this entire table with zeros for now, because I know in the long run I'm going to add into it. So 0 is a great starting value. That being said, I have a really important seed value. I need to make sure that my table at index 0 actually starts as 1, right? Because there is one way to make the empty string, right? Then from here I can start my core algorithm by just iterating through every position of the table. So set I equal to 0, go up to and including target dot length, and hit every index, right? And so what I'll do is iterate through every word of the word bank. So let word of word bank. And as I iterate through every word, I need to check if the word matches my current location, right? If it has aligning characters. So you've seen this pattern before. I'll check if target.slice. I'm going to slice some characters out of my target, starting at index I, right? Because I is my current position. I need to look at the next couple of characters based on the length of my word. I'm going to slice I to I plus word.length. Cool. So my current position is I. This will give me the next word.length number of characters starting at position I. So I'll check if that little segment is equal to the word I'm considering right now. And if it is equal, then I have a word that I can actually take. I can modify some further position of the table. In particular, what I should do is I need to modify my table at index I plus word.length. So I'm looking ahead. Remember that our current position is I, so I'm looking ahead in the table based on my current word's length. What I want to do is actually increase that by some value. I want to increase it by the number stored in my current position, right? That's what we did at every point of the algorithm. Nice. A common mistake that I see students make is usually they have a tendency to just increment by 1 here, right? That's not the move. What you want to do is increment by exactly the number that's in your current position, right? And at this point, I think all we need to do is just return our final answer, which, like we always know, is basically table at target.length. Cool. So I have some examples below with their expected results. Let's give this a shot. Count construct. So I get 2, 1, 0, 4, and 0. Notice that we have a fairly large example which should return 0, right? You can't possibly generate this final F here because your word bank only contains a bunch of E's. And it ran fairly quick. So this solution's looking pretty good. Notice how small of a variation it is from our last problem. Hopefully you're really feeling the progression. So let's kind of quickly just take a look at that. That was our can construct problem. So let me split these guys. Very, very trivial difference, right? Instead of assigning a true value, now I actually just increment because I have numbers within my table. That was short and sweet. Let's head back into the drawing board. Let's do one more problem together. Let's revisit that all construct problem. So we're still taking in our target string as well as an array of words in a word bank, but this time you want to return all of the ways that you could construct the target by concatenating elements of the word bank. So here you need to return a 2D array. That means a single element of the array represents one combination that makes the target. And like usual, we can reuse elements of the word bank as many times as we see fit. So if you take a look at an example, let's say I gave you the target of A, B, C, D, E, F, and I gave you this array of words. You actually have many ways to create the target string. There are 4 ways over here. So each subarray represents one combination, where if you concatenate it together, you get the target. And so notice that I want to return every single combination as an element of the outer array over here, right? So if there are many ways to create something, then I want to return a 2D array. That being said, there are a few examples that we should keep really in mind having to do with our seed values that we kind of foresee, right? So let's say I gave you this example where your target is the empty string and I gave you just some words in the word bank. The point is, since your target string is empty, your result should really be a 2D empty array. So recall that the outer array here represents like the collection of multiple combinations, and here there's only one combination that makes the empty string, right? So the inner array represents like that empty combination when we take no words of the word bank. And this is a reasonable thing to do because let's say I gave you this example. If your target was birds and I gave you an array of cat and dog, then the result there should be just a one-dimensional empty array, right? The array over here represents the collection of combinations, and there are no elements here, right? There are no combinations that ever yield birds. So we'll keep those sort of seed value base case scenarios in mind. So let's trace through this example of A, B, C, D, E, F. I'll start by initializing our table. We're going to need a lot of room in this one. And so we know that the size of this table is going to be based on the target string, right? Just like we usually do. And then we have to figure out what our seed values are. And we kind of just spoke about them. We know that if I have the empty string, then I need to have a 2D empty array. And so we'll initialize that in our table. I know we're going to need a lot of room, so I'm going to spread out these outer brackets. Now for all of the other elements of our table, we want to make them just one-dimensional empty arrays. And here's the reason why, right? For these further values in the table, I have to actually check for ways to generate them. So for now, there are no ways that I've found, right? That's why I just have an array with 0 combinations inside, except for index 0, right? Index 0 has one combination inside that happens to be the empty combination. Cool, so let's start with our general algorithm. A lot of this logic will feel very similar to our last 2 problems. Now we're just adjusting it to generate these combinations, right? So we know that we're going to try to visualize how we look at our string in terms of some prefixes, right? I know that if I'm highlighting some spot in my table, then that grabs the prefix starting at index 0 all the way up to but not including my current index of the table. And I'll light up those characters at the top over here. So what I need to do now is, since I'm currently at index 0 of my table, I consider words of my word bank that have matching characters from this position. So I can look at this AB first. And if I took this AB move, then I should look 2 characters ahead, right? Because AB has a length of 2. So that brings me to this position in light blue. And what I should do is take all of the combinations in my current location in yellow and actually copy them over into this future position. But when I do that, I also need to be sure to include in those combinations the move of the word I just took, right? So that would just be adding an AB inside, right? So again, kind of repeating that step, I copy over the contents of my current position in yellow, but then I have to make sure I add my word that I'm consuming right now into each of those combinations I just added. Cool. And now we would actually keep our current position here because there are still some other words of the word bank that have matching characters, right? I can take an ABC from this position. And something very similar happens, right? I copy over my current array. and then I go ahead and add ABC to it. This happens one more time for ABCD. Awesome. At this point, I've considered all of the words that match from this current position, so I can move forward a little bit. At this point, though, I need something that starts with a B, right? Because my current position has a B on it. And I actually don't find any words of the word bank that kind of match from this position. So I actually can move my current once more. When I'm at this position, I have to consider words of the word bank that have a C, right? And there are a few that I can use here. I can use CD, right? And if I do that, I look 2 characters ahead, or 2 indices ahead from my current position. So I'm looking at this index. So if I look at index 4, I have a really interesting situation, right? I already have some combination stored inside of index 4. And that represents one way we could make ABCD, right? By just taking that lone word ABCD. But what I can also do is I should take all of the combinations from my current position and just add them into that index 4, right? So I'm taking the AB from index 2, just adding it to index 4. But then I also need to add to that new combination the word I'm using right now, which was CD. Cool. And then from here, you already noticed that, hey, there are so far 2 ways to create ABCD. You can just take that lone word ABCD, or you can do AB plus CD. So this logic is taking some nice shape here. For my current position, there's actually one more word that matches. It's really just a single character C. So like I do, I look 1 character ahead or 1 index ahead in my table just next door, and I copy over the combinations from my current location in yellow, but then I also append the word I'm consuming, which is just an additional C, right? So far I have 2 ways to make ABC. At this point, I can progress my current spot in the table, and I look for any matching words that start with a D, right? So that would be the DEF over here. DEF has a length of 3, so I look 3 spots ahead in my table, and I need to add some information here. I copy over my current combinations in yellow, and then I have to append at the end of all of them the DEF word that I'm using right now. So it looks like this. At this point, I can iterate my current position. So now I'm at index 4 as my current, and I look at any words that start with an E. And there's actually just one over here, just this EF. And so I look 2 characters ahead, or 2 indices ahead from my current position. And again, this is a scenario where I need to append new combinations to this existing list, right? So if I look at my current position at index 4 in yellow, I'm going to take all of those combinations and copy them over into my light blue position at index 6. And then from there, I also need to make sure that I append to them the word I'm using right now, which is an EF. So those 2 combinations also get an EF at the end of them. Nice. And at this point, you see our final result at the last spot in the table. If we continued the general algorithm, we would just move our current position to index 5, where there's actually no words that could start with an F over here. So nothing happens on this iteration. And there we have our algorithm, right? That index 6 of the table contains all of those 4 ways we described that we can use to create our original target string. Take a moment to look at this table and notice how every position of the table should make some logical statement about the target string. Right, I can see that if I chose some position, let's say index 3, that's giving me some information about the substring ABC, right? That prefix of my original target. And what it's saying is there are 2 ways to make ABC. You can just take ABC, because that's actually a word of my word bank, or you can do AB plus C, right? That's the only other way. That applies for all positions within my table. If I look somewhere else, like at index 5, that means I'm writing some information about A through E. And if there's no combinations at this position, that means there's no way you can ever generate A, B, C, D, E. And if you take a quick glance at the words in the word bank, that is correct. You can't possibly just generate A, B, C, D, E. So overall, the information in our table and our logic that we did was very consistent. Before we hop into the code for this one, let's do the analysis. So we know that M is going to be the length of our target string, and we'll define N to be the number of words in the word bank. So like we described when we did the memoization and recursive solution for this problem, we really can't do better than a sort of brute force, right? Because they're asking us to return literally every single way to generate our target string here. So really the time complexity is going to be the shape of an exponential, right? So about n to the m. Again, it will have some extra like multiplication terms of m in it, but overall we're looking at an exponential time complexity. And what's the reasoning behind that? Well, we know there's going to be an exponential number of actual combinations that we need to return. And I have to actually construct all of those combinations piece by piece. And so I'm looking at least exponential time. And really, once something gets exponential, that's really the limiting factor, right? In a similar way, we can say that the space complexity for this is also going to be exponential, again, roughly. We know that we're going to have at least m space just from the straightforward size of the table, but notice that every element of the table itself is going to be a 2D array. So in a sense, we're really dealing with like a 3D table in this instance. And so we know that at any particular position of our table, we're going to have potentially an exponential number of things, right? If you consider the very last spot in our table, just the last spot, that already has an exponential number of combinations inside of it. But then I would actually have that throughout my entire table. So it'd be really a little more than just n to the m. But overall, I'll say it's roughly exponential complexity. And you can't really do any better here, right? Especially in terms of the time. I'm really asking you to just do this in a brute force way. And I think we'll actually be able to see that once we create the solution. Let's hop into it. All right, for one last time, let's solve this all construct problem. So I'll begin by creating my table. By now we're tabulation master, so this is very, very formulaic. Create my table with roughly target size, really target.length plus 1. And here I need to initialize the elements of my table as arrays. So here I need to be very particular and make sure I get a unique array in every spot of the array. So I'm going to do a fill. We've seen the syntax before. And then I'll map over it. That way I can generate a new array for every element here. Cool, let me just style this up. And so this should give me an array as every element of my table. Right? Notice that the elements right now are just one-dimensional empty arrays, right? These arrays represent the collection of combinations. At the start, they're empty, meaning that I have no combinations for most of these elements, except for one, right? We already spoke about table at index 0, right? That should be a 2D empty array. And the reason was, still the outer array here represents the collection of combinations. For the empty string, there is one combination that you can use to make it, right? And that is the empty combination where you take no words of the word bank. Cool. So now I can begin my general algorithm by just iterating through my target. We've done this many times before. So I'm iterating through my table. And what I'll also do is look at all of the words, right? So on every iteration, I'm going to consider some words of the word bank. So I'll say let word of word bank. And like before, I still need to check that, all right, these words better have matching characters based on my current position. So I'll use that classic logic, right? I've seen it many times by now. And I'll slice a segment out of my target string. I'll say target.slice starting index I and grabbing the next word.length number of characters. Cool. I'm going to compare that chunk to the current word that I'm iterating through. Nice. So using this if statement, I'm sort of filtering down all of the words and only going to do some logic on the words that match based on my current position. Nice. And so we've seen, this nested for loop and if statement before, right? Now we're adding our new logic within this if statement. Cool. All I need to do is really understand what types of data I'm dealing with here. All right. So let's say I just wrote this expression, table at index I. What that's going to do is just reference my current spot in the table. And if I think about what data it's going to be, it's definitely going to be an array, right? It's either going to be like an empty array, meaning there are no ways to make this current target, or it could be a multi-dimensional array, where every subarray represents one way I can make the current target. So if this is all of the combinations that generate my current, then what I'll do is I'm going to map over them. Remember in our drawing, what we did was kind of copy over all of our current combinations, but then make sure we also add our word that we're using right now to the end of each of those combinations. So that's what I'm doing right here. I'm going to map over every subarray. And what I'll do is I'll just copy over the elements of that subarray using that spread syntax that we've seen before. And then I'll also be sure to add on at the end my word. Nice. And then that will give me, let's say, our new combinations. So I'll just say that to a variable maybe. So new combinations is going to be a 2D array, right, where every subarray represents some combination. And I want to take these combinations and add them into that further spot inside of my table. So I know I need to kind of look ahead in my table. So I can look at table at index I plus word.length. And I know that all positions of the table are going to be arrays, right? So this is going to be an array. There's going to be some data that might already exist at this position, right? So what I don't want to do is just assign new combinations, because then that would overwrite any previous existing combinations that I already found for this position. Instead, I need to make sure that I just add these new combinations to that list, right? So what I'll do here is I'll push to that array, and I'll push all of the elements of my new combinations, right? So here I can spread this out. I'm going to spread it out, that way I don't add any additional nesting over here, right? So this is looking pretty good. I think let's go ahead and return the table at target.length. Here I have some examples down below. Let's give this a shot. Nice, and these answers look correct, right? Notice that these last two examples should return empty arrays because they are impossible to generate. Cool, so let's hover over this code for a moment. Probably the most tedious logic here would be these two lines, right? Really try to understand how like these two lines translate into the logic we did in our drawing. So let's break down these lines again, right? Line 11 is going to take all of the combinations in my current position, in my drawing that was like my yellow box, and it's going to add our current word to each of those combinations. And then we're going to take each of those new arrays and add them to the list at our further position, right? Being sure not to overwrite. We already spoke about the complexity of this one. It's definitely going to be exponential, probably a little more than exponential, right? If you imagine all the work we have to do using these maps and like spreading, we have to actually construct our result array, which is going to contain an exponential number of things, right? So even if I look at this last example, let's say that I made it a little longer, right? So let's say I actually blew up the size of that input. It's going to be very, very slow, might even crash, but let's just do it. So let's say I had a bunch of A's here, just for fun. So if we try this example, yeah, it looks like our program still crashes, right? This is going to return a really massive array. Probably can't even fit it into memory over here, right? We still get like a stack size exceeded, even though this isn't even recursive, right? Just calling functions way too much over here. So no matter what we do, we really expect this problem to sort of demand an exponential solution. With that, let's head back into the drawing board where we can wrap up this course. All right, programmers, by now we solved many different dynamic programming problems together, and I want to leave us with some final advice. So whenever you're starting to attack any dynamic programming problem, start by really taking a moment and noticing any overlapping subproblems. And then from there, really focus on like the input to the problem, in particular its type. And from there, you should be able to recognize what is the trivial smallest input. So in our string problems, usually that means the empty string. In our array problems, it's the empty array. Or in our number problems, it's usually a number like 0 or 1, right? Is there some input where we don't really have to do any extra work to know the answer? The answer just sort of is what it is. Once you've recognized this trivial scenario, or the base case really, then you'll want to realize how you can relate this base case toward your larger inputs. And then you have two options, right? You can either think recursively and use memoization, or you can think more iteratively and build a table using our tabulation formula. I think as you practice dynamic programming problems, I would actually always solve problems in two ways, one using memoization and one using tabulation. Then of course, from that point on, it's okay if you have like a favorite strategy. For me, personally, that's memoization, but that being said, it really helps to have options when you're in an interview. And once you've made that decision on, which route you're going to take, definitely, slow it down and draw a strategy first. This is, I think, the most important thing about just data structures and algorithms in general. Usually when we draw our pseudocode or draw our process on the whiteboard, we can recognize all of these edge scenarios, and it's much harder to do when we just write like the code out of the gate. And so I promise if you slow it down and take a moment to draw a visual, you're going to find your work a lot more productive, as well as more intuitive when you explain it to someone else. And of course, through all of that, you're going to have a lot more fun, dealing with these quite hard topics. All right, programmers, that's all I got for this course. Hopefully you had fun, learning this new topic. I definitely had fun teaching it to all of you. So what you want to do now is head down to the links in the description and head to coderbyte.com where you can actually practice this new topic. Thanks for watching, and I'll see you in the next one.